Okay, so these are the reactions that you will learn about. So the key thing is nucleophilic, there's going to be a lot of nucleophilic addition, right? So that results in the carbonyl bond being transformed into two sigma bonds, right? So in terms of the bonds, you have 1 pi, 1 sigma. Here you have 2 sigma. Okay, so just remember that you need to always have an aqueous acid. The reaction is irreversible, and these metal stuff are really reactive. They react with water. That's how reactive metals work, and so you need to be doing it in dry conditions. Dry just meaning no water, so you can do it in an organic solvent, whatever. Okay. Definition of reduction. They're just using this reduction of aldehydes and ketones as an example of how nucleophilic addition works, because the first step is that. Just for info, reduction is the gain in hydrogen, right? So that's why R is commonly interchanged with H for organic chemists. Okay, so what's next, right? So this can be a bit weird, the mechanism, so just bear with me on that. So this boron, right, has a negative charge on it. It has a negative charge because you have formed this additional bond, right? So interestingly enough, you would probably think that it attacks like that, right? The answer is no, by no means, right? Because think about it, remember, this has 4 bonds. Okay, so 4 bonds means that all of the 2p subshell is filled up. You're not going to be able to attack and form a new bond. So instead, what happens? You will get this H bond attack there. Okay, you'll get this H bond attack there. Then you will have this go up, and weirdly enough, this comes down, which is probably easier for me to represent like this instead. Okay, so what I'm gonna get is this. Oh, is it like that? Okay. What I'm gonna get is like that. And sorry, yeah. So this negative charge. No, sorry. This is not a lone pair of electrons. That's just him showing the formal charge of boron. Yeah. So that happens, and then when you have your BH3, what it's gonna do, right? I'll draw it out like that. Right? These electrons here are gonna go in there. And that's what you see here. Okay, so I'm just gonna highlight that. So I'm gonna highlight that. This bit here like that. It forms this bond. Okay? And then afterwards you just do some protic workup and you end up with that. Okay? Nothing too bad. Next, reversible. Oh, okay, NaBH4 is weak, so it's not going to reduce esters or amides. It will only reduce most reactive carbonyls because this bond breaking process is not very. This is not a very strong nucleophile, right? So that means that the carbonyl must be reactive. Okay, so it's just like how electronics, going back to electronics, right? This guy doesn't have a lot of Riz, right? He doesn't have much game. But if this carbon over here is thirsty enough and if this carbon guy is thirsty enough and he sees like a 5 out of 10 with no game, right, then he's just gonna let it happen, right? So that's what happened. So if esters or amites, right, the guy is not as desperate. So if a 5 out of 10 approaches him, he's not gonna hook up with the 5 out of 10. Okay? So reversible nucleophilic addition, hydrate, hemiacetal, ketal. Okay. So how far the equilibrium lies towards hydrate or ketone depends on the reactivity of the carbonyl. The rate of nucleophilic addition can be increased using catalysts. Okay, aldehydes and ketones form hydrates. Water acts as a nucleophile. So water it's an okay, not very good nucleophile. So so it's important that you will have so it's important that you have a desperate guy basically if the girl is not, has no game, right? So that's gonna happen, and that's how you end up with this positive charge. And yeah, so then after that you're gonna get another water, right, that will cause that to happen, right? And then you will grab another you will grab something else to oh yeah, you will just grab the other guy will grab these, and that goes back, and then you have your water again. So yeah, so in this case, you will have, yeah, that water is helping you on the side. Okay, so similarly, this process happens again. The outcome is different for base or acid catalysis. So it's important to look at the mechanisms. Okay, so using that, you're gonna remember that oxygen has 2 pairs of electrons like that, and that is what attacks. Again, alcohol, not very good of a leaving, not very good of a leaving group, not very good of a nucleophile. I say again, not very good of a nucleophile, but simply because the guy is so desperate, he's gonna get together with this, he's gonna hook up with this alcohol, right? And because the alcohol is now with this guy, it has an extra charge. Again, our friend water is gonna come down, grab this, and then these bonds go back, and that's how you end up with that, right? Oh, sorry, not water. You need base, and I realized they've just drawn the base here. So that happens, and then you have H plus and base. And then the thing is, because the base can't take up another proton, so you can only stop at the hemiacetal. Your base would normally be something like pyridine, and so once it's taken up that extra charge like that, you physically can't do that anymore. You're not going to get back the base, and that's just going to be consumed during the reaction. It just doesn't make sense. Okay. Same goes honestly for other things like hydroxide. If I use hydroxide, right, it's the same thing. I have water. It can't accept anymore. Okay, so if you have you have decomposition, it's the same process basically. So